I'm Anil Kumar. Welcome to my series on Combinatorics. We'll now discuss the method of induction to prove statements. It is a very important method and can be used whenever you're looking into cases where natural numbers is the set of domain. Now we'll prove by mathematical induction few statements. I've taken 8 examples which are from previous test papers, and I hope that is going to help most of the students. Now let us understand these steps involved to use this particular method. Well, step number 1 is to show that the given statement P of n is true for n equals to 1. And step number 2 is to assume that the statement P of n is true for a natural number m, then show that it is true for m plus 1, right? So that we assume that it is true for one natural number somewhere in between the range, and then we have to prove using that information that the next n value also works. The algorithm here is first statement always should be clearly write down the statement which we need to prove, right? Sometimes that is tricky. So clearly write statement, which is P of n in our case, and understand its meaning. Then we have to show that P of 1 is true. Then we have to assume that P of k is true. Using this assumption above, that is P of k is true, we need to prove that P of k plus 1 is also true. Perfect. Now, combining the above results, that is to say that we know that the statement is true when the natural number 1 is substituted, when any natural number k is substituted, and when the next natural number k plus 1 is substituted. That means it is true for all the natural numbers. So that is how we are going to conclude that the statement is true on the set of natural numbers, right? That is kind of important. But in many examples, you'll find that the initial value, which we are putting as 1, could be 0 or something else. It is kind of transforming the statement. Do you understand the point, right? So here is a very important note, which is mathematical induction is a method to prove that a statement P of n is true for every natural number, right? That is how we normally say it, right? We can always modify and extend it to integers by taking the initial value as 0 or even a negative instead of n equals to 1. Consider step 1, which is n equals to 1, as the initial condition in general to extend the application of the method of induction. So if you need to, you could actually do that sometimes, right? So, but carefully, you could do that. Now let's take up the examples and see how to apply this algorithm. Very first question for you is to prove that 9 to the power of n minus 2 to the power of n is divisible by 7 for all n belonging to natural numbers. So we'll follow the statements first. First we have to make a statement, right? A clear statement. So let the statement be that P of n, so we are now using this statement P of n is equal to 9 to the power of n minus 2 to the power of n is divisible by 7. So that is now our statement, right? We need to prove this, however, but that is the statement which we need to prove. That's the whole idea. So we are writing a statement which we need to prove. So P of n is equals to 9 to the power of n minus 2 to the power of n is divisible by 7. We need to prove this statement. Now what are we going to do? First, we'll check for n equals to 1, that is P of 1. So if I substitute 1 here, we get 9 minus 2, which is 7, and sure, this is divisible by 7, correct? So we say P of 1 is true. So for n equals to 1, the statement P of n is true. Now we'll assume that it is also true for n equals to k. So P of k is divisible by 7. That's what we are saying. Now divisible by 7 means what? Means that It is a multiple of 7, correct? So that really means that P of k, which is equal to 9 to the power of k minus 2 to the power of k, should be equal to 7 times k, a multiple of 7. Only then it is divisible by 7. So that's kind of, tricky. And that is how you have to look into it, correct? Now, what are we supposed to do? We are supposed to check for P of k plus 1, n equals to k plus 1. That is what we would like to check. So replace n with k plus 1, and what you get here is 9 to the power of k plus 1 minus 2 to the power of k plus 1. Now, using the exponent laws, we could write this as 9 to the power of k times 9 minus 2 to the power of k times 2. Well, we can rearrange and write 9 as 7 plus 2, right? Do you see that? So what we did was that we wrote 9 as 7 plus 2 in the first term. And that helps us to take something common, correct? So that helps us to take something common and simplify. So we have this particular statement that now when you expand this 9 to the power of k times 7 plus 2 times 9 to the power of k, and we already have 2 times 2 to the power of k. And clearly you can see that 2 can be taken common, and we get the other factor, which is 9 to the power of k minus 2 to the power of k. And that factor is known to you, right? So that factor is known to you as 7k. So we are going to substitute this particular value as 7k. So once you do that, right there, you can see that 7 is a common factor, and now you can factor 7 and write this as 9 to the power of k plus 2k times 7. Now clearly it's a multiple and multiplied by 7. Therefore, pk plus 1 is also divisible by 7, right? So that is how we are going to prove it. And concluding remarks is very important. Pk plus 1 is also true, and so 9 to the power of n minus 2 to the power of n is divisible by 7 for all n belonging to set of natural numbers. Is that clear to you? So you have to provide all these reasonings when you're proving by the method of induction. Otherwise, you will definitely lose quite a few marks. Now here, let's look into question number 2, which is kind of similar, but a different algorithm altogether. So, which is prove that 1 plus 4 plus 7 plus so on. So this is a series where we are adding by 3 each time. Arithmetic progression, correct? Arithmetic series, I should say, we are adding them up. Plus 3n minus 2 equals to half of n times 3n minus 1, correct? Plus for all n belonging to natural numbers. Clear? So it is sum of an arithmetic series which is definitely increasing by 3. And so we have a final sum, right? We need to prove this is true. Correct. So again, we'll begin with the let statement, and P of n is the statement which we need to prove. Then we'll check for n equals to 1, substituting 1. What we get here is just this 1. And also in the formula, when you substitute 1, we get 1 times 3 times 1 minus 1 divided by 2. And that is also 1. So we know that P of 1 is true. It stands for both left side and right side. Now we are going to assume that let P of k be true. Substituting k here, we get P of k as 1 plus 4 plus 7 plus so on till 3k minus 2. And that should be equal to half of k times 3k minus 1. And that becomes our equation, which we are going to use later to prove that P of k plus 1 is also true. Perfect. So that is the whole thing. But what is P of k plus 1? In the result, we will replace n with k plus 1, and that's what we need to prove. So this is what we need to show. Okay. So let's begin with P of k plus 1, replacing the last term with 3 times k plus 1 minus 2. Remember, the second last term which you have here is P of k. So this is P of k, and we're going to replace this with what we just found, that P of k, rather assumed that P of k is true. So we're going to replace this by half of k times 3k minus 1, and that's what we did here. And we'll copy the other one right away. And now it's a question of simplifying and getting into the required form, right? So now, to do that, well, let's do one thing. So we have to simplify the other term, which is right there. Let's open the bracket. And once we open the bracket, we do see that there is something in common, and that should be factored out. So let's take half as common. If nothing is there, let's take half as common, right? So we'll multiply the other term, 3k plus 1 by 2. So we get 6k plus 2. So when you multiply this term by 2, we get 6k plus 2. We took half as a common factor. Now we have a polynomial within our curly brackets. So in that simplifying, we get a quadratic function which can be factored. Once you factor that, you get a form which is very close to your answer. But it is very important to give the exact answer and see how we manipulate it. We have written pk plus 1 as equal to half of k plus 1, right, which is already there, k plus 1, and 3k plus 2 has been written as 3 times k plus 3 minus 1. Do you see that? So here we have 3k plus 2. So we want something like this. So we wrote this as 3k plus 3 minus 1. That is what we did. And so we could now factor 3 and write this as k plus 1 minus 1 as shown right there. Is that clear to you? So that is how we kind of match it with the required value. Perfect. And then we say, well, it works for k plus 1 also. Since it works for k plus 1 also, we have shown that the statement is absolutely correct. And so we have a concluding statement right there which says P of k plus 1 is also true. And so this particular statement, P of n, is true. Now let's look into the next question. Here we are going to work with sum of squares, a very popular question. Question number 3 for you. Prove that 1 square plus 2 square plus 3 square and so on plus n square is equal to a very standard formula, 1 over 6 times n plus 2 times 2n plus 1 for all natural numbers. Remember, we are always working for all natural numbers, correct? Now again, we'll start with the let statement and we'll redefine the whole thing as P of n. So that is let statement saying that this is our statement which we need to prove by the method of induction. First step, let n equals to 1. When you substitute 1 here, what do we get? We get 1. Also in the formula, when I substitute 1, then what do I get? I get 1 over 6 times 2 times 3, which is 6. That also gives me 1, correct? And so we know that it works for the value 1. Now we'll assume that it will also work for k. So substituting k here, as you can see, the last term will be k squared, and in our product, every n will be replaced by k. So 1/6 of all that. We need to show that for k plus 1 also the statement is true. Replacing k with k plus 1, we get this particular statement which we need to prove. Now let's begin by substituting k plus 1 on the left hand side of our statement, which is 1 square plus 2 square plus 3 square plus k plus 1 whole square. As you can very clearly see, the first terms up to k square is what we assumed, and so we're going to replace it with that particular formula, right? So this is what is being replaced. Now that plus k plus 1 whole square should be simplified to show that it is equal to the right hand side for k plus 1. So we'll now see what can best be done. Well, last time we did half common factor, so this time let us see what best can be done. Well, k plus 1 is also a common factor this time, so now we can take 1 by 6 times k plus 1 as a common factor. Rest all goes into our curly brackets, and there you have a quadratic equation as we see last time, as we have seen last time, and that can be factored. Once you factor that, it becomes simpler to arrange and write in the form required. Do you see that? So we split this term again, the last term, to show k plus 1 plus 1. Do you see that? And then we kind of match with what is required to be matched. And we once again prove that P of k plus 1 is also true, and therefore the statement given to us is true for the set of natural numbers. Perfect. So we are already halfway through. Now let's look into question number 4. Now in this particular question, I like you to read the question, pause the video, and then answer this. This is very similar to our previous example, alternating squares. Earlier we had all these squares, correct? So now we need to prove that 1 square plus 3 square plus 5 square and so on, odd numbers, 2n minus 1 whole square is equal to 1/3 of n times 4n square minus 1 for all natural numbers. Again, the process is same. First statement, P of n is what we need to prove. Then n equals to 1, substitute 1. 1 square is 1. And on the right side, what do we get? 1/3 of 1 times 4 minus 1, which is 1/3 of 3, which is 1. So both left side and right side are 1 for n equals to 1, so it works. Now we'll assume that it also works for k. So n equals to k is being substituted, and so that is equals to 1/3 of k times 4k squared minus 1. We need to now show that it is going to work for k plus 1 also, and the expected formula is given here for reference. So that is what we need to prove. Okay, clear? Now let's begin to simplify the statement. So replacing k plus 1, you get this statement, and as we have seen all the time, the first few terms now can be replaced by the assumption, right? So these can be replaced by the assumption which is right there, and this assumption replaces, and then we have the sum of the last term, right? So this part here is the assumption. Correct. Plus 2 times k plus 1 minus 1 whole square. Now we can actually take, in this particular case, 1/3 times this. We can actually factor 4k square minus 1. So if you factor 4k square minus 1, we get these two factors, which is 2k plus 1 times 2k minus 1. And now you can see that 2k plus 1 is a common factor. So we can factor 1/3 of 2k plus 1, and then within our brackets we can simplify the polynomial expression, and once you simplify that, which is right here, you get a factored form, and now you can rearrange and get the required result. That's the whole strategy, correct? So we get 1/3 of 2k plus 1 times 2k squared plus 5k plus 3. 3 times 2 is 6, we need 5, so that means 3 times 2 can work. So we split it into 3 times 2, and then we refactor it. So these are the steps required for factoring. Once you have done the factor, we see that 1/3 of k plus 1 is a common factor, and within the brackets we get 2k plus 3 times 2k plus 1. Well, still, it is not really matching. We need to have 4k plus 1 whole square minus 1. That's what we need. So once again, we expand this, and once we expand it, we try to perfect square this 4k square, and then we split. And so the two terms with minus 1 there, and as you can now see that we are in a position to write the first three terms as 4k square minus 1, right? That is how we'll do it. So we do get 4 times k plus 1 whole square minus 1 as a common factor there, and then 1/3 of k plus 1 was already there. So we have shown that it works for p k plus 1 also. So the statement is now again true for the value k plus 1, and therefore we can conclude that the statement is true for all natural numbers. But writing that statement as we have written here is kind of important, right? So that is how you should finish it off. Here is question number 5. Now in question number 5, I'd like you to read the question, understand the strategy, and then we'll look forward into its solution. Question number 5 is, prove that 1 times 2 times 3 plus 2 times 3 times 4 plus so on, n times n plus 1 times n plus 2 is equal to n times n plus 1 times n plus 2 times n plus 3 divided by 4. Right? Kind of average of the four values. So that is what we're looking into, right? Okay, now, first statement is to write the statement itself, which is P of n is whatever we need to prove. Common. Second, n equals to 1. When n is equals to 1, we get 1 times 2 times 3, which is 6. And on the right hand side, again, when we substitute, you get 6. So it works for n equals to 1. Now we'll assume that it works for k also. Substituting k, we get that the left side is equals to k times k plus 1 times k plus 2 times k plus 3 divided by 4. Now, we need to prove that this statement should also work for k plus 1. Replacing k with k plus 1 is what we need to show. So this is what we need to show, right? So let me highlight this in blue. Now let's start working with our statement on the left side, which is p times p of k plus 1 is 1 times 2 times 3 plus 2 times 3 times 4. It ends with k times k plus 1 times k plus 2, which is the previous term, and the new term additional is k plus 1 times k plus 2 times k plus 3, right? So here there's one additional term which is not supposed to be there. Correct. So we have three terms, right? So that's what you get. Now, what we will do here is that we have this term is additional here, right? Okay. Now, you can take 1/4 common. So 1 over 4 is taken common here, and then multiply the other term by 4, correct? So we multiplied this term by 4. So we have two terms in the numerator from where you can take the common factor. The common factor is k plus 1 times k plus 2. What remains is uh, k plus, okay, so common factors k plus 1, k plus 1, and k plus 2, k plus 2. These are the common factors. What remains is k times k plus 3. Okay, k plus 3 is also common, right? So we took all the three terms as the common factors, and what remained was actually k plus 4, correct? So that remains k plus 4 divided by 4. So this is what was expected. So if you look into what was expected, we got exactly the same terms. So now we have shown that it works for k plus 1 also. Since it works for k plus 1, then the statement is true for all natural numbers. You see how we are repeating the same steps and very easily proving our statements. Now, this is not an easy job. So one is you have to get an idea about what this could be, and from there you can actually prove using the method of induction. Now we'll look into some reciprocal functions. So we'll have question number 6 is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, so on, plus 1 over n times n plus 1 should be equal to n over n plus 1. Now you can actually derive at this particular result also. Sometimes the question will be estimate what is the sum of the series and then prove it by the method of induction, right? That remember that part. So it could be this also, okay? Now, let statement, this is the statement which we need to prove, n equals to 1. When you substitute 1 here, you get half as your answer from both the sides, and so it is true. Substitute k and say, well, this statement will be true. And we are going to use this statement to prove that k plus 1 also is true. So for k plus 1, we substitute k plus 1. So we get k plus 1 in the numerator and k plus 1 plus 1 in the denominator. So for k plus 1, when I substitute the first few terms, I should say all the terms except the last one, adds up to the assumption, right? So adds up to the assumption, which is k over k plus 1. And we're left with the second term there with us. Now, as you can see, 1 over k plus 1 is a common factor. So in the brackets, we get k plus 1 over k plus 2. Then we can just cross multiply and now simplify it. Once you simplify, you get k plus 1 over k plus 2. However, we have to write this in the required form. So I have split k plus 2 in the denominator as k plus 1 plus 1, right? And so we have shown that it works for k plus 1 also, and therefore it is true for all natural numbers. Now again we have a reciprocal function, but this time as a sum. So now we are saying 1 plus 1 over 1 plus 2, 1 over 1 plus 2 plus 3, and so on till 1 plus 1 plus 2 plus 3 plus 4 till n should be equal to what? 2n over n plus 1 is what we are expecting for all natural numbers. Okay. Now first statement is p of n is what we need to prove, and we now prove by setting up n equals to 1. Once you put n equals to 1 in this particular statement, you get what? You get 2 over 1 plus 1, which is 1, and therefore that is the answer, right? 1 in both left side and right side, right? And now we'll assume that it is also true for k, right? So we'll write k instead of n and then use this statement to prove that it is also true for k plus 1. So we replace k with k plus 1 and we have an additional term here. Previous terms, sum is known to us, right? This is known to us. So we're going to replace with the known result and the new thing, and then we have to take something in common. Well, one thing important is, the sum of natural numbers is what, right? So these are the natural numbers up to k, which could be written as half of k times k plus 1. And that 2 goes in the numerator, and so we could write this as 2 on the top, k times k plus 1, and the other term, which is 2 times k plus 1. Since we took half multiplied both by 2, correct? And so we get that. And now we can take 2k over k plus 1 and 2 over k plus 1 times k plus 2. We do clearly see a common factor, which is 2 over k plus 1, and what remains is k plus 1 over k plus 2. And this can be simplified. We'll just cross multiply, and then we are going to factor this. It is a perfect square, k plus 1 whole square. And clearly what you notice here, that it could be simplified. And when you cancel, you get what? You get 2 times k plus 1 over k plus 1 over 2, right? So that's what you do. Yeah, I forgot to write 2 here. So I should have written 2 here. Okay. So we get this as 2 times k plus 1 over k plus 1 plus 1. And now we have shown that it works for p of k plus 1 also, and therefore it works for all natural numbers. Is that clear? Now, here is the last question. We began with the divisibility rule. We'll end with the divisibility rule itself. But see, in between, there could be many types of questions which will be like what we have dealt with. Now, here is a strategy. Prove that x to the power of 2n minus y to the power of 2n is divisible by x plus y, right? For all n belonging to natural numbers. First statement, P of n is what we need to prove. Then n equals to 1. We get what? N is 1, we get x squared minus y squared, which is x plus y times x minus y. And it is divisible by x plus y. So we have shown that. So we have shown that for 1, it works. Now we have to show that it should work for k plus 1. But then for pk, we'll assume it to be true. So when pk is there, what we get here is x to the power of 2k minus y to the power of 2k equals to a product of x plus y. So we are using a constant u in this particular case, and we are saying x to the power of 2k minus y to the power of 2k is actually equals to x plus y times u. Is that clear to you, right? This is a very critical step here. Okay, so it is a product of x plus y. Now, we need to show that pk plus 1 is also divisible by x plus y. So, what is pk plus 1? Replace the exponent 2n, where n is now replaced by k plus 1. So I straight away wrote 2k plus 2, right? K plus 1, when you open the bracket, you get 2k plus 2. Now you should understand, when I'm writing 2k plus 2, x to the power of, right? So it really means x to the power of 2k times x squared. Perfect. Okay. So to further go around, we know we have to use this particular result. So why not get a term like this as a common factor? How do we do that? So here is a strategy. This is a very important strategy. We added and subtracted x to the power of 2k y squared. You see that? So adding and subtracting the same term doesn't change the part which we are working with, right? So the equation remains the same. Now, but it helps us to factor. Now, if I can combine two, I can take x to the power of 2k as a common between the first and the third terms. Let me just show it which ones we are taking as common, this and this, correct? So when I take these two terms, what I get is right there, x to the power of 2k gives me x squared minus y squared. On the other hand, I am taking these two terms common, right? With minus y, and that is what I'm getting. Minus y squared is x to the power of 2k minus y to the power of 2k. And now you can see we can split x square minus y square as the product of sum and difference. So this is written as the product of sum and difference, and clearly we do have a common factor here, which is x plus y. So x plus y has been taken as a common factor between these two. Correct? So once you do that, and you can, and okay, now one more step in between was our assumption was that this is equal to is a product. So it is x to the power of 2k minus y to the power of 2k is x plus y u. And therefore, this particular term has been replaced by x plus y u. Do you get that step, right? So we have done that. Now x plus y now is a common factor, correct? So we have taken x plus y as a common factor. This is not there. So once you do that, what you get inside the bracket is x to the power of 2k times x minus y minus u times y squared. That's what you get, correct? Now, you can clearly see that x plus y is a factor, and it works for pk plus 1 also. And therefore, once we show that it works for pk plus 1 also, we have shown that the statement is true for all natural numbers, and that is how we are going to do it. I hope you found this exercise useful and interesting. Now, I'd like you to write down your comments and suggestions. If you need to get in touch with me and to learn from me, you can always send an email on the given address. You can also put in some good marks on my website, which is globalmathinstitute.com. Thanks for your time and all the best.